Hello everyone, welcome to today's ECA Technical Tuesdays webinar with Curtis Jones from our technical team. So this session will look at exploring protection against overload. Please feel free to ask your questions in the question box and we will put these to Curtis at the end. So this session is being recorded and it will be uploaded to our YouTube channel in the next couple of days, and you can download a professional development certificate for attending today's webinar. Details of how to access this will be available at the end. So thank you, and over to you, Curtis.
Thank you, Kat. Good morning, everyone, and welcome, or good afternoon, everyone now, sorry, and welcome to this presentation where we're going to look to explore protection against overload. Okay, so on to the agenda for today's presentation. We're going to start things off with an introduction on today's topic. We'll then move into looking at the principles of overload protection. We'll look at positioning of devices for protection against overload, and then we'll look at some scenarios and examples where we may actually admit devices for protection against overload. And then, as always, we'll finish off with a summary and some time for some questions that may come up throughout the presentation. Just to point out, this is sort of a high-level overview of what we're going to cover off today. So there will be some other pieces of information wedged between some of the high-level points here. It is quite a big topic regarding overload protection. You can go really quite deep into this when we consider designing circuits and confirming overload protection. So we're not going to go into big depths in terms of design. Some things we won't cover is that we'll outline some and recap some basic formulas that would need to be considered, but we won't go into in-depth design of circuits for protection against overload, including that of things like motor control. On top of that, the session is focused on overload. Of course, what sort of goes in hand with that is protection against fault current. We won't be going into major depths with regard to protection against fault current. We see this as part of a bigger topic. It will be referred to within the presentation, but we're likely to pick that up in more depths in a future presentation. And I guess a little bit of signposting before we start today's presentation. In terms of looking at some more in-depth calculations and examples, we do have, of course, some guidance documents in terms of the IET's design guide and the guidance note 6 that do provide some good calculated examples which may be relevant for a bit of further reading. Okay, introducing myself initially, as mentioned, I'm Curtis Jones. I'm one of 3 technical managers that sit on ECA's technical team. A little bit of a background on myself. I came into the industry a short time after leaving school as an apprentice. I worked in the field in various backgrounds, typical industrial, commercial, domestic backgrounds, and particularly built quite a strong experience with regards to inspection and testing. After a number of years off the tools and prior to joining the ECA, I came off the tools, I should say, and I worked in education and training for a few years, where I mainly worked to deliver the apprenticeship program for aspiring electricians, as well as many courses on the wiring regulations and many courses on inspection and testing. On top of that, I had quite a lot of involvement with regards to design of projects and systems, which of course includes selecting devices for protection against overload, a topic we're going to focus on, of course, today. Aside from my day-to-day duties at the ECA, the role also allows me to be active in the development of various electrical and technical safety standards, primarily BS 7671, and I'm a member of one of the subcommittees, JPAL C64, which mainly focuses on protection against electric shock. And within that scope, we also look at protection as covered in Chapter 53 of BS 7671. And of course, the ECA, we are the UK's largest electrical trade association, with members turning over around £6 billion combined annually. So hopefully the topic we're going to cover off today ties into a lot of the works that members cover, particularly when designing and verifying systems. Okay, jumping into today's topic then and introducing it. So I think it's best to start off probably recapping for the initial few slides and starting with a few definitions. So of course, part 2 of BS 7671 provides us with definitions that are commonly used throughout the standard. So the first one I want to start with is an overcurrent, and part 2 tells us that an overcurrent is a current exceeding the rated value. And for when we consider for conductors, the rated value is the current carrying capacitor of the conductor, which is generally information we would obtain from Appendix 4 of BS 7671. So with regards to an overcurrent, there are 2 types of overcurrent. The first one is due to a fault current, so a current resulting from a fault condition. So that typically being, let's say, a short circuit condition. Of course, that would generate a large amount of fault current generally, which is going to cause a rapid disconnection, hopefully, of the relevant protective device, overcurrent protective device. Now, of course, there is another type of overcurrent, which is an overload current, and this is where we're going to focus around more today within the presentation. So the definition of an overload current within BS 7671 is that it is an overcurrent occurring in a circuit which is electrically sound. So when we say it's electrically sound, it's not subject to, for example, a short circuit condition generating a significant amount of current very quickly. So when we look at overload conditions, common causes of an overload are due to either the user of the installation causing the condition, or potentially an overworked piece of equipment. So when we consider the user of the installation, it may be that they connect additional equipment, so much so that the current now exceeds what the circuit was originally designed to carry. And this, of course, could either be by a deliberate action or an accidental action from the user. And then an overworked piece of equipment, I think the common example of that could be a motor or a machine, which of course they are prone to overload due to their nature. They could be, for example, subject to a mechanical fault, which could cause an overload condition. So in terms of when we have overload conditions, we select protective devices to protect against that circumstance. Now, I've placed on screen some common overload protective devices. This isn't an exhaustive list. There are other types of overload devices listed within BS 7671, but I felt these are sort of the most common devices as we can see on screen here. When we look at overload protective devices and their operation, this is generally achieved by thermal devices. That meaning that they take up a period of time in order for them to activate and disconnect the circuit. So taking a circuit breaker, for example, if the level of current was to exceed the rated value of the circuit breaker, it's going to start to heat up the bimetallic strip within the circuit breaker, and then after a period of time, it's going to cause the device to activate. Obviously, the more current, generally the faster the device is going to activate. Now, for some devices, particularly BSEN 60947-2 devices, some potentially are molded case style circuit breakers, Some devices are adjustable, and BS 7671 requires that they must be sealed or constructed so that alteration cannot be made without the use of a keyer at all, as per requirements of Chapter 53. So hopefully that lays the basics of what an overload is and shows some examples of typical overload protective devices that we select within installations. So a bit of a recap. I think sticking with a recap, just laying out some of the principles of overload protection. Now, typically in most circuit designs, we provide protection against overload. That isn't exclusive, it's not always required. And we will be running through some examples and some requirements that may allow you to omit overload protection a little bit later. But in typical circuits, in most circuit designs, we do provide overload protection. And the reason we do this is to protect the cable should the load current increase above its intended design value. So we place our overload protective devices to stop thermal damage occurring to a cable within a circuit. Now, in order to do this, circuit designs should follow the requirements of Regulation Group 433.1, and that initially tells us that circuits should be designed so that small overloads of a long duration are unlikely to occur. And we will refer to that final bullet point a little bit more. And Regulation 433.1.1 looks at coordination between conductor and overload protective devices, and it initially provides us with three indents. But I'm initially going to run through the start of the regulation and indents 1 and 2 to start with. So it states that the operating characteristics of a device protecting a conductor against overload shall satisfy the following conditions. Number 1, the rated current or current setting of the protective device, IN, is not less than the design current, IB, of the circuit, and indent 2, the rated current or current setting of the protective device does not exceed the lowest of the current carrying capacities, IZ, of any of the conductors for the circuit. So quite a wordy requirement, but fortunately we can simplify this into a formula to break it down and make it a little bit easier to understand. So those first two indents to Regulation 433.1.1 essentially give us this formula, and that is IB is less than or equal to IN, which is less than or equal to IZ. So breaking that down into two sections then. So we firstly look at IB, which is the design current of the circuit, which of course is the current to be carried by the circuit within its normal operation. Should be less than or equal to IN, which is the rated current or current setting of the protective device. So hopefully pretty straightforward, and I'm assuming this is probably a recap for most. The circuit that's going to, the level of current that's going to run within the circuit in its normal operation should be less than or equal to the rating of the protective device, and that of course then would prevent the protective device becoming overloaded and potentially activating and disconnecting in its normal operation. So hopefully straightforward enough. The secondary half of this equation, IN, the rating of the protective device again, should be less than or equal to the IZ, which is the current carrying capacity of a cable for continuous service under the particular installation conditions concerned. So here we're looking at the cable needs to be able to carry at least the amount of current that the protective device is rated at. So essentially that would mean that the protective device is going to protect the cable and essentially, after a certain time period, disconnect to prevent the thermal damage occurring to the cable. So we're rating our cable for the maximum possible current that could circuit. Now, I want to drill down a little bit deeper onto the term IZ, because it's often a term that is misunderstood within industry. So I did just have the definition up on screen, which told us it's the current carrying capacity of the cable for continuous service under the particular installation conditions concerned. So what does that really mean? Well, it's based on many things, really. It takes into account how the cable's installed, so that could be the installation reference method, whether it's single phase, three phase, and then also any factors that will affect its current carrying capacitor. So I've got on screen here Formula A. So Formula A breaks down what IZ may equal. So this is an example. So I've placed on six rating factors here as an example, but there are others. It's not an exhaustive list, and at the same time, it's not likely that you're actually going to have six affecting one particular circuit design generally. So the IZ would be equal to IT. Now, IT is the tabulated value of current carrying capacitor, and that would be as per the tables in the back of BS 7671 in Appendix 4. And that IT value would be times by any applicable rating factor. So, for example, we may have a grouping factor, which would be CG, which may then derate the tabulated value of current carrying capacitor to give us our IZ value. Now, looking at this Formula A still, as we could see, IZ and IT would only ever be the same if any of the rating factors were 1. And that is essentially the only way that these values would be equal to each other. Now, IZ is a term that is used within the normative parts within BS 7671. So we've just looked at Regulation 433.1.1, which refers to IZ. However, when we size cables, we often apply rating factors as divisors to IN, as we can see here within Formula B, when we're looking to ensure we achieve protection against overload. So often we apply Formula B instead of Formula A, because it helps to avoid the process of trial and error and repeatability when we're selecting cable sizes in order to achieve IZ is not less than or equal to IN. So we're essentially ensuring this part of the equation. So a quick example, let's say, for instance, I had a 32 amp protective device protecting my circuit. I was looking to pick a cable size, and I went to the tabulated value within Appendix 4 for a particular cable type, and it told me it carried 34 amps. So I'd think, great, I'll pick that cable size, but then I apply, let's say, a grouping factor to it of 0.8. That's then going to take this IZ value below the 32 amp rating of the protected device, and then I'm going to have to go back and try a different cable size. So often we apply Formula B because by applying Formula B, we take the rating of the protected device, divide it by applicable rating factors. Like I say, this isn't an exhaustive list. That way, then we get a value of current that we need our cable to be able to carry as a minimum, and then we select it from the tabulated values within Appendix 4. So that's a method that we could consider when we're looking to protect our cable against overload. Okay, As touched on, there is a third requirement to Regulation 433.1.1. Now, I'm mainly going through this requirement for information because it is only a requirement to perform this additional calculation in certain situations, as we'll see in a minute. So I'll firstly go through the formula. So again, indent 3 is another wordy-ish requirement. So I've simplified it into a formula. That being I2 is less than or equal to 1.45 times IZ. So what that means is we've got a new term we've introduced here. I2 is the current causing effective operation of the overload protective device. Now, these values aren't as such within BS 7671. It would be a device, it would be a value of current, the I2 value, provided by either the product standard. So if you had a circuit breaker, BSEN 60898, as an example, or by the particular manufacturer of the protective device that you are using and selecting. So what we're essentially saying with that formula, that I2 value would need to be less than or equal to 1.45 times the current carrying capacity of the cable for the particular installation conditions concerned. So taking in into consideration any applicable rating factors. So the factor 1.45, it's based on a combination of experience and investigation. And this has shown that types of cables that are considered within BS 7671, they can safely withstand a small but undefined number of periods at excess temperatures corresponding to currents not greater than 1.45 times their current carrying capacitor. So BS 7671 accepts that the cables could go beyond their maximum operating temperatures, but it is essential that these such currents do not persist for long periods. So just referring back to something I mentioned a moment ago, is we should ensure when we design circuits that overloads of long durations do not occur, and we will drill down a little bit deeper onto that one in the coming slide. And we'll also look at an example regarding I2 values. Now, as mentioned, this third requirement, we often don't need to perform this. That's because regulation tells us, regulation 433.1.201 tells us that this requirement, indent 3, it is fulfilled for some devices. So for some, if your circuit's protected by, for example, a circuit breaker to BSEN 60898, providing you fulfill indents 1 and 2, so the previous formula that we've just been through, then compliance with indent 3 is also fulfilled. So that applies to circuit breakers, and it also applies for certain fuses, and that's detailed within 433.1.201. However, for some circuits and some protective devices, further consideration is required. So for example, if you've got a BS 3036 fuse, this would require some further consideration, and that is covered within regulation 433.1.202. And that's because the current causing effective operation of BS 3036 fuses is considerably larger. I think it's around 2 times the rating of the device. Additionally, cables buried also require some further consideration, and that's covered within regulation 433.1.203. So I think to sort of summarise this one, this indent 3 is essentially another part to the puzzle to protection against overload. But where we use our most common types of protective devices, there's nothing else we need to consider, providing we've achieved the requirements of indents 1 and 2. Okay, so I've mentioned a couple of times small overloads of a long duration. Of course, again, touched on this already, but overload protection is achieved by thermal devices. That meaning generally they take up a period of time to heat up in order to cause disconnection. So the current needs to go beyond the rating of the protective device. And then depending upon how far beyond the rating of the protective device it goes, it's going to take a sustained period of time, for example, to warm a bimetallic strip up within a circuit breaker and cause the disconnection of the device. Now, devices such as circuit breakers to BSEN 60898, and this example in the table being based on type B and C devices at a current rated less than or equal to 63 amp. So devices such as these have what we call a non-tripping current, and this is signified by I1. And in this case, the non-tripping current is 1.13 times the rating of the circuit breaker. And what this means is that the circuit breaker should not operate at this level, 1.13 times its rating, within the conventional time. And in this example, the conventional time is 1 hour. Now, we also have what we call the tripping currents, the I2 value, something I referred to on the previous slide. And in this case, it's 1.45 times the rating of the circuit breaker. Hence, we don't need to be concerned with the third requirement, which I've just gone through. Now, when tripping current levels achieve I2, and they are and become present within the circuit, the device must then operate within the conventional time. So a bit of an example here, if we had a 10 amp type B 60898 circuit breaker, it should not trip within 1 hour at 11.3 amps. So taking it from a cold condition, then applying 11.3 amps through the circuit for 1 hour, the device shouldn't activate. Taking the same 10 amp device, that must trip within an hour with the presence of 1.45 times its rating, 14.5 amps. So this sort of highlights up hopefully how a circuit breaker works in terms of its operation and what is required by the product standard for the design and makeup of a circuit breaker. Now, fuses are similar and they operate on, instead of a non-tripping current, a non-fusing current, and instead of a tripping current, it would be a fusing current. So similar, but obviously slightly different terminology. And of course, the values that we've got on screen here are specific to circuit breakers. Fuses would have different values. And again, the IET design guide, it has got a detailed table similar to this, but with a lot more examples of typical devices that we find in common electrical applications. So small overloads, I've mentioned that a fair bit, and regulation 433.1 does state circuits shall be designed so that small overloads of a long duration are unlikely to occur. Now, if we have small overloads of long durations, it is of course going to cause the conductors to increase beyond their maximum permitted operating temperature, so say 70 degrees for typical cables that we use. And this, in turn, it's not going to have a short-term effect, but what it could mean is that it's going to cause aging and deterioration over a number of years to the insulation surrounding the conductors and potentially to connections due to this increase in temperature. Of course, we accept that overloads may happen from time to time. We've only got to consider when we initially switch some equipment on, but we should avoid this where possible as part of the circuit design, and we certainly need to avoid it for long durations. Now, the term long durations, I'm not aware of a definition for this, but from a bit of reading, and I know that the IoT design guide refers to this, is that it is likely to be classed as a duration in excess of the conventional time. So we have to consider with cables, they do take up a period of time to heat up with the load present in the circuit. So it's not something that is going to instantly happen if they start to be beyond their intended design value. Okay, so switching focus now to ring final circuits, and this again is something covered within 433, 433.1.204 in particular. Now, as we know, ring final circuits for many years have been a commonly used circuit for socket outlets within the UK. Now, ring final circuits, they're a little bit of a special case in that we look to minimise the risk of overload. So as per that regulation, they're required to be protected either by a 30 or 32 amp protective device. Regulation also requires for copper live conductors that they're a minimum CSA of 2.5 millimeters squared. And then the IZ value is to be at least 20 amps. So again, this is quite an interesting one, and I would say one that is sometimes a little bit misunderstood. So as we know, typical rings wired in 2.5 millimeter live conductors. Some people assume, being on a 32 amp device, that the cable would need to be rated for at least 16 amps. But what that doesn't allow for is that the load on the circuit may not always be evenly shared. Of course, when we design a ring final circuit, we need to consider and do everything we can to try and allow for reasonable sharing of the load. But the IZ being at least 20 amps does take in a little bit of consideration of that. Another requirement within this regulation, the load current in any part of the circuit should be unlikely to exceed the IZ value for long periods. So again, we see that term around long periods again. So essentially, we need to consider what the likely loads are going to be on the circuit and look to avoid the IZ values, the current capacity of the cables being overloaded for sustained periods of time. Of course, Appendix 15 of BS 7671 provides some additional guidance to achieving compliance with this set of regulations. And again, we need to consider how we would design a ring circuit to confirm the compliance with that. So a bit of a signpost to Appendix 15 there as well, but these are sort of the high-level points for ring final circuits. Okay, a quick point on electric motors. And electric motors in excess of 0.37 kilowatts require control equipment to protect against overload. So we're not speaking about equipment that's plugged in here. We're speaking about dedicated fixed electrical pieces of equipment, being motors. So in order to protect the motor against overload, we need control equipment for that. And this is, of course, often achieved by the motor starter, which would generally include an overload relay to prevent an overload condition within the motor. Okay, so hopefully that's sort of the main points around overload protection. And we're now going to look at some requirements where we move away from what we essentially generally do in most circuit designs. So we're now going to look at positioning of devices for protection against overload. So focusing first what we generally do, I guess I haven't quite covered this one off yet. So where we have a reduction in current carrying capacity of conductors. So essentially, a cable is connected that is smaller in most cases. Then an overload protective device is often required, and generally we provide it. And that is a requirement of regulation 433.2.1. So if we think of how we are supplied just into our homes, we have a suitably sized cable coming in from the distributor, and we may have, say, an 80 amp fuse placed within the service area. We then connect in with suitable sized tails into the consumer unit. And then, of course, from that point, we look to connect individual circuits, which would often have a reduced cross-sectional area. So then we typically provide overload protective devices to protect those circuits. However, overload protection can be achieved by installing the overload device downstream of where a reduction occurs. Now, this example would be particularly common with a busbar chamber, so maybe what we see in sort of this example on a photo here. So we'll look at that in a bit more depth in a second. So this regulation, or in order to place the overload protective device downstream of where the reduction has occurred, so maybe where our cables have become smaller, it requires compliance with regulation 433.2.2. Now, high-level information included within this regulation. It tells us there shall be no branch circuits or outlets between the point of reduction in current carrying capacitor and the protective device. So there should be no branches between where the reduction has occurred and where the protective device downstream has been replaced. And it is required to be either protected against fault currents as per section 434, or length not exceeding 3 meters, and is installed in a manner to reduce the risk of fault, fire, and danger to a person to a minimum. Just to point out, I've said all there. It could be both if you wish, but it's got to be at least one of these conditions. Now, focusing on the image we've got on screen here, which one of my colleagues kindly provided me with. So from information I've gathered from this particular installation, there is a 200 amp supply at the origin of the installation. And then we can see there are suitably sized live conductors coming from that origin point and connecting onto the busbar chamber. And then if we see probably the best example, tapping off the busbar chamber to the right of our screens here, we can see there is a reduction in current carrying capacitor. These cables look considerably smaller than the ones here at the origin. And these cables then come off into some 100 amp fuses. So we've gone from a 200 amp supply, suitably sized cable, smaller cables, 100 amp fuses. So we've essentially placed these fuses downstream of where the reduction in CSA has occurred. Now, without knowing, I would imagine we've likely achieved compliance with protection against fault current as per section 434. I'm not going to drill down too deep into that, but as sort of a high level overview, it's likely that if a fault was to occur, let's say between these cables, that it's going to cause a sufficient fault current to disconnect the upstream fuse before, and the upstream fuse would then disconnect before thermal damage would occur to these reduced conductor sizes. The other option, of course, is the length not exceeding 3 meters, which this also looks to fulfill, and is installed in a manner to reduce the risk of fault, fire, and danger to persons to a minimum. So locating the wiring in an enclosure manufactured from a non-combustible material would certainly be a measure to reduce to a minimum the risk of fire or danger to persons. With regards to the risk of fault, this may achieve it. It's a very short length of cable, or it could be seen that maybe this would be more suitable to have a double insulated cable coming down to this point, and that of course would then further reduce the risk of a fault condition between those points. Okay, so that's an example of where we look to essentially place an overload protective device downstream, and this is quite a common question we get through to our ECA technical helpline, and part of the reason I've likely put the presentation together today. Okay, next we're going to look at omission of devices for protection against overload. So as already discussed, often we do provide protection against overload for most circuits, but BS 7671 does recognise the option to admit this. Regulation 433.3 highlights that this shall not be applied in installations that present a fire risk or risk of explosion, or where installations or locations specify, special installations and special locations specify different requirements. Providing that bullet point 2 isn't a concern and that is fulfilled, Regulation 433.3.1 provides us with some options in admitting overload protection. Now, the first one, essentially, I've titled this Omission of Devices for Protection Against Overload, because that's where it sits under in BS 7671. Essentially, overload protection is provided here. What it essentially does is allows us to not provide further overload protection. So it's that high-level information from this regulation. Conductors which are situated on the load side of the point in which a reduction in current carrying capacity occurs don't require further protection if the device on the supply side effectively provides protection. So taking, for example, a lighting circuit, which may be protected by a 6-amp circuit breaker. It may then be wired in 1.5mm squared singles in a conduit, for example. And then there could be a situation where a ceiling rose is then connected, and the flexible cables coming down from the ceiling rose may be of a reduced cross-sectional area of 0.75mm flex, but providing this flex was suitably rated, say for the 6-amp protective device, then it essentially would be effectively protected against overload. So no further requirements for an overload protective device, as one example. Now, some circuits, and this is covered within indent 2 of 433.3.1. So some circuits contain loads that are fixed, or they are not liable to overload, and therefore overload protection can be admitted in its entirety. So this could be for loads such as maybe an immersion heater, or for lighting where the load is known, and there is reliability that for the particular piece of equipment or circuit that there is no way it can overload beyond its design value for the circuit. Now, where this is the case, we would need to ensure that protection against fault currents in accordance with section 434 is required. So again, we would need to ensure that for the circuit, although it may not be protected against overload, if due to there being no chance of an overload happening, we would need to confirm that if a fault condition was to happen, so for example, a short circuit was to happen, that the conductors could safely deal with the level of fault current flowing through the conductors for the required time for the protective device to operate. So the cables don't get thermally damaged. Okay, again, we have been asked about this one occasionally on the helpline. So overload can be admitted for certain loads where there is no possibility of an overload condition. Now, where this is the case, of course, I had this formula up on screen a little bit earlier. However, there's one subtle change in that when we protect a circuit against overload, when designing the circuit and selecting the cable size, we often do IN divided by applicable rating factors. But where we're not protecting against overload, it would be the design current divided by any applicable rating factor. Okay, and the third requirement for regulation 433.3.1 now, and again, this is more of a case of not providing further overload protection. So often further overload protection is admitted at the origin of the installation up to the main distribution point where the distributor's device is relied upon. And we've got a typical example of this in a domestic setting here. This, of course, comes with some restrictions regarding the lengths of the tails from the origin of the installation. If, of course, the DNO's requirements are exceeded, then further overload protection would be required. So if your main distribution point was not at where the origin of the installation entered, so you say 10-15 meters away, then we would be required to provide overload protection to protect that cable from the origin. Okay. So there are also some examples where we may admit overload protection for reasons of safety. So overload protection may be admitted for some circuits supplying specific current using equipment where the unexpected disconnection could either cause damage or danger. Now, there is some examples listed within BS 7671 within regulation 433.3.3. Again, I've just sort of simplified this. So circuits that are supplying a safety service. So this could maybe be a sprinkler system, maybe a life support equipment, on maybe an IC earthing system, maybe some kind of fire alarm or some kind of fire extinguishing device. So circuits for safety services. And then we have circuits supplying a lifting magnet. Of course, disconnection in some cases could cause danger, so you would need to confirm with the manufacturer of the lifting magnet whether there are controls built in where maybe this isn't a consideration. And then the secondary circuit of a current transformer, which of course could potentially cause damage. Where this is the case and overload protection is admitted for one of these reasons, then there should be consideration to the provision of an overload alarm. Okay, so to finish off with a summary, sort of high-level points. Overload protection is generally applied in most of our circuit designs, typically when we design circuits. And of course, the main purpose of this is to prevent thermal damage to our live conductors. However, as we've seen with some of the examples, BS 7671 does offer some flexibility around overload protection in some circumstances, which includes either placing protection downstream of maybe where a reduction in current carrying capacity has occurred. So particularly useful where we have busbar chambers, or even admitting it in its entirety, maybe where we have particular loads that are not prone to an overload condition. Okay, and that is it. So I'll open up to see if you have any questions. I believe CPD certificates will be sent out. Is that right, Kat?
Yes, so I'm going to drop a link in the chat, but it'll also get sent to the email that you signed up with to join this webinar.
Yeah.
Yeah, thank you very much for that. We don't have any questions at the moment, but I'll give it a couple of minutes for that.
Okay, no props. Mark got a light in there.
Yep, got a question here.
Okay.
Necessary to provide overload within a dwelling with fused isolator on consumer tails. I think that's larger than 3 meters when the fuse size is 60A and selectivity would be an issue due to maximum demand and let through energy could not be achieved.
Okay, interesting question. With regards to, I think a little bit cut out then, but I think that it was mentioned that you're going to exceed the distributor's requirements. It's going to be more than 2 or 3 meters, whatever the distributor's allowing. On that basis, if the distributor's requirements are exceeded, then yes, I would say a device is required. I wouldn't be concerned with selectivity. I would say it's a requirement to provide a device. So essentially, you may look at a 60 amp device, but I wouldn't say you've got to achieve selectivity. Otherwise, you're essentially going to need a larger supply in some cases just to try and achieve selectivity. Within installations, selectivity can be partial. So I wouldn't be concerned with selectivity in that case. I would just look to provide the fuse, so we have a fuse within the consumer's installation as per the requirements of BS 7671. The DNO's fuse is primarily concerned with protecting their equipment as such. So yeah, I wouldn't concern yourself with selectivity in that example. Okay.
Hopefully that answered your question, Daniel.
Yeah.
Haven't got any more questions.
Okay. Yeah, I mean, if Daniel, if he wants a bit more or further discussion, feel free to email the helpline or ring the helpline, and we can go through it a bit more and have a chat about that.
We've got another question. So, on a UPS system, can the inverter on the UPS be used as a protective device, or a MCB/fuse MCCB is required to meet the disconnection time, overload protection, and short circuit protection?
Sorry, could you repeat? I don't know if I grasped all that question. Do you want to repeat it? I'll try and.
Yeah. On a UPS system, can the inverter on the UPS be used as a protection device, or a MCB/fuse MCCB is required to meet the disconnection time, overload protection, and short circuit protection?
I've fully followed the question. I've not fully got the question, to be honest. Maybe if you can email me that, and I can sit and read it for a few minutes, I might get my head around it. It might be because I'm hearing it and I'm not digesting all the wording. And send me the contact details of the person, or if they're wrong the system, I can email them back. I'll probably get my head around it a bit more if I've got it in writing in front of me, and I'll reply. If not, I'll contact the person and we can have a chat.
Yeah, we'll pick up with you after.
So
another question. How would you decide if a C-type or D-type MCB is required for a compressor motor drawing 13.3A?
13. I guess you would have to look at the level of inrush current that is present upon startup, and then you would need to consider whether that level of current is going to activate a C-type device, or whether it's going to sit below the levels of instantaneous current that's going to disconnect it. So essentially, you're going to be relying on data from the manufacturer or off the compressor equipment itself, so you're aware of what the level of current's going to be on that switch on. It is going to make that decision for you. So ultimately, you need information to confirm, because I think, as the person's pointing out, yeah, if it's in excess of what would disconnect to C automatically, you're quite right. Then yeah, it's not really suitable. So information is sort of the answer to that one, I think.
Okay, thank you. Just see if we've got any more questions coming in or any follow-ups to anything you've said. Obviously, if anyone does have any questions afterwards, they can just get in touch with you on the technical helpline.
Yeah, feel free to call in or email. And yeah, if you can send me that one straight through, I'll have a proper look at it and a read, see if I can.
Yeah.
I don't think I'm taking it in fast enough.
No. Do we have any guidance notes or any documents that we can send out to people after related to this?
I will. A good question, and I will have a look at that. And I probably should have checked before, but I'll be honest, this is likely to get turned into a guidance note at some point. Often when we do presentations, we often spin them into a guidance note, you know, so people have got something documented, people learn different, of course. So no doubt that there will be a guidance note on overload in the future. And to be honest, for a guidance note, we may encompass fault currents as well within that. So it may be part of a bigger guidance note. As I mentioned, I might look to do some non-fault current in the future. So it may be part of a bigger guidance note. But I will have a look what we've got on the system. But it's probably one on the to-do list.
Yeah. But in the meantime, obviously, this is recorded, and so people can go back and have a look through and see all the slides. We've just got another question. Is bidirectional RCBOS a requirement or a recommendation to solar PV installs, or is it only for battery systems?
So with regards to, there's a few layers, I guess, to that question. So solar PV, there's possibility of bidirectional energy flow. You would need a bidirectional protective device for that example. Now, there isn't a specific requirement within section 7112, which of course is the special installation requirements for solar PV systems. Now, there isn't a specific requirement for solar PV, so the AC supply to the inverter for the solar PV circuit. There's no specific requirement for RCD protection. So it may be that you can design out the requirements for an RCD. So it may be that you can protect it by a circuit breaker, for example, and then you would just need to confirm that in that case that the circuit breaker was suitable for bidirectional energy flow, which I believe most of them are. So hopefully that answers the question. And I mean, the same would apply for any circuit where there is the possibility. I know batteries was mentioned. The same would apply for that. Of course, if you've got installation requirements that then necessitate the need for an RCD, so it could be that you've got inadequate fault protection, or maybe on a TT earthing system or something, or you may require additional protection for the circuit because of the installation method or whatever else. Then you would have to consider that the RCPO or RCD, whatever you'd selected, was suitable for the bidirectional power flow. That was enough.
Thank you. Right, I think that's all we've got time for. So thank you, everyone. Obviously, get in touch if you've got questions. And thank you very much for joining. All right.
Brilliant. Thanks a lot. Cheers.
Bye-bye.
Bye-bye.